Welcome to This Explainer. I am absolutely thrilled you're tuning in today because we're stepping totally out of the ordinary and straight into the laboratory. Go ahead and mentally throw on your lab coat because for this session, you are a chemical detective. Today, we're opening up the Chemical Detective's Manual to completely demystify organic chemistry. We're going to learn exactly how to interrogate unknown compounds and correctly identify the usual suspects in the lab.
Which brings us to a really fundamental question. How do we actually tell these organic compounds apart? Think about it for a second. Molecules are entirely invisible to the naked eye. We can't just stare at a beaker of clear liquid and say, oh yeah, that's definitely an alcohol, or yep, that's a hydrocarbon. We are literally flying blind without the right tools. So to uncover their true identities, we have to rely on very specific chemical interrogations that give us real sensory clues we can actually see and smell. Okay, let's dive into this. Our primary tools are what we call distinguish tests. Basically, these are specific chemical procedures we use to differentiate organic compounds based on distinct, undeniable physical observations. We're talking about dramatic color changes, the sudden appearance of cloudiness, or even very distinct, sometimes pretty intense smells. These physical reactions, they're basically the fingerprints of our chemical suspects.
Here is the exact roadmap for This Explainer. First, identifying unknowns. Then, tests for alcohols and amines, followed by spotting aldehydes and ketones. Next up, behind the scenes with mechanisms. Then our Hall of Fame for name reactions, and we'll wrap it all up with chemistry and the real world.
Section 1, identifying unknown organic compounds.
We're kicking off our forensic work by focusing on hydrocarbons to figure out if they're saturated or unsaturated. And to test for unsaturation, we rely heavily on sensory signposting. Take the bromine water test. We start with this incredibly vivid orange-red liquid. If we mix it with our suspect and that bold color instantly disappears, boom, we've got an unsaturated hydrocarbon. Or there's Bayer's test using alkaline potassium permanganate. We start with a really bright pink. If the compound is unsaturated, that pink just vanishes entirely, leaving behind a muddy brown precipitate of manganese dioxide. Seeing these bold colors disappear instantly grounds the abstract chemistry into a reality you can literally see.
Now, if our initial tests narrow our suspects down specifically to alkynes, well, we need some specialized interrogation tactics to make the final ID. To spot a terminal alkyne, we bring in the heavy hitters, Tollens reagent or ammoniacal cuprous chloride. These reagents react very specifically with that terminal hydrogen, giving us a highly unique reaction that confirms our alkyne suspect without a shadow of a doubt. Section 2, tests for alcohols and amines. All right, we've got hydrocarbons down, so let's move on to our next class of suspects. The Lucas test is a brilliant way to differentiate alcohols based entirely on one factor, speed. We treat our mystery alcohol with Lucas reagent, which is just a mix of hydrochloric acid and zinc chloride, and we watch for turbidity or cloudiness. The results follow this perfect rhythmic rule of 3. Tertiary alcohols, immediate turbidity. Secondary alcohols, turbidity takes about 5 minutes to show up. Primary alcohols, the solution remains completely clear, no turbidity at all. It's essentially a precisely timed confession from the molecule itself. We actually use a really similar rule of 3 pacing to sort out amines, but this time using the Hinsberg test. Here, we shake our amine suspect with benzene sulfonyl chloride, and the sorting mechanism is based purely on its solubility in an alkaline solution. Primary amines, they form a soluble sulfonamide. Secondary amines, they form an insoluble precipitate. And tertiary amines form a totally different soluble addition product. So just by observing what dissolves and what doesn't, we can instantly identify our amine.
Section 3, spotting aldehydes and ketones.
Let's keep this momentum going and examine carbonyl compounds, because I promise you, the visual clues here get even more dramatic. If you're trying to identify an aldehyde, you use tests that yield absolutely stunning physical results. With Tollens' test, warming an aldehyde with an ammoniacal silver nitrate solution literally produces a brilliant, reflective silver mirror coating right on the inside of the test tube. Honestly, it's one of the most beautiful reactions you'll see in chemistry. Alternatively, Felling's test yields this thick, reddish-brown precipitate of copper-1 oxide. Both are just undeniable, highly visual confirmations that you're looking at an aldehyde.
And if we want to get really specific, we run the iodoform test. This is our giant red flag for any compound containing a methyl group bonded directly to a carbonyl or a hydroxyl group. So we're specifically talking about 2 ketones, 2 alcohols, ethanol, and ethanol. If this exact structural motif is present in your suspect, the test throws out these vibrant, bright yellow crystals of iodoform. It's impossible to miss. Section 4, Behind the Scenes Mechanisms.
So far, we've identified what happens, but as true chemical detectives, we need to understand why it happens. We need to interrogate how they react at a microscopic level. Now, what's really interesting about this slide is the stark contrast between these two incredibly famous substitution mechanisms. On the one side, the SN2 mechanism is a fast, one-step, direct nucleophilic attack. The nucleophile strikes right from the back, instantly kicking off the leaving group. But on the other side, the SN1 mechanism plays a much slower game. It requires a slow, deliberate first step to form a stable carbocation intermediate before the nucleophile can even swoop in.
Let's trace the path of another classic mechanism together, the hydration of an alkene to form an alcohol. Just follow the flow of electrons through these 3 critical steps. Step 1. The alkene grabs a proton from a hydronium ion, which forms a carbocation. Step 2. A water molecule acts as a nucleophile, directly attacking that positive charge. And finally, step 3, another water molecule steps in to remove that extra proton, yielding our final neutral alcohol. It is just a beautiful, perfectly logical dance of electrons.
And this brilliantly illustrates the esterification mechanism. This is exactly how we combine a carboxylic acid and an alcohol to form those sweet-smelling esters. The absolutely crucial thing to note here is the tetrahedral intermediate sitting right in the middle, and how careful proton transfers allow the reaction to actually proceed. Also, check out the equilibrium arrows at every single step. That reminds us that esterification is a completely reversible process.
Section 5, Hall of Fame, Name Reactions. Okay, we've seen the mechanics, so let's meet the absolute legends of the lab. These are the specific foundational reactions that completely revolutionized organic synthesis. First up, the aldol condensation. This one requires an aldehyde or ketone that possesses at least one alpha hydrogen. When you put them under the influence of a dilute base, 2 molecules of ethanol, for example, will condense together. They physically link up to form a much larger, way more complex beta-hydroxyaldehyde. It's an incredible, elegant way to build larger carbon frameworks from tiny building blocks.
But wait, what if your aldehyde doesn't have an alpha hydrogen? Well, that creates a completely different scenario, the Cannizzaro reaction. Molecules like formaldehyde or benzaldehyde lack that crucial alpha hydrogen. So when they're hit with a strong, concentrated base, they literally cannot condense. Instead, they undergo this totally fascinating self-redox disproportionation, effectively splitting their fates. One molecule gets reduced into an alcohol, while the exact same type of molecule gets oxidized into a salt of a carboxylic acid.
Next up in the Hall of Fame is the Gabriel thilamide synthesis, which is this highly reliable 3-step method for synthesizing perfectly pure primary amines. The logic here is just so elegant. Step 1, you treat thilamide with alcoholic KOH to form a potassium salt. Step 2, introduce an alkyl halide, which attaches your specific carbon chain right to the nitrogen. Step 3, hydrolyze the whole shebang with dilute HCl to release a beautiful, completely uncontaminated primary amine. Section 6, Chemistry in the Real World.
All these tests, all these complex mechanisms and named reactions we've covered, they aren't just abstract puzzles drawn on a chalkboard. It is time for the "so what" portion of our explainer. So the crucial point is that mastering these molecular manipulations has a massive, undeniable human impact. Just look at haloalkanes for a second. Chloramphenicol is a synthesized antibiotic used to treat typhoid fever. Thyroxine is an iodine-containing hormone that treats goiter. Chloroquine is a critical synthetic halogen compound used to fight malaria. And halothane, it's been widely used as a life-saving anesthetic during surgery. Literally, this chemistry cures diseases and saves lives every single day. Which brings us to our final thought for this explainer. You've seen the tests, you understand the underlying mechanisms, and you now know the profound impact these synthesized molecules have on global health. If mastering these foundational chemical rules allows us to solve microscopic mysteries and engineer life-saving drugs, what real-world problems could you solve next by applying this exact same knowledge? Keep questioning, keep investigating, and I'll see you in the next explainer.